So first, hello everyone, and I want to apologize for not being able to come to Paris. I had COVID a few days ago, so it was a bit complicated to organize a trip. So, but I want to thank the organizer for letting me present my work in remote. So today I want to talk to you about observation we made about the Pipe Nebula with my PhD supervisor. And I will mainly focus on the dense core of this region with turbulent and which is a turbulent and magnetized region. So first I will present the Pipe Nebula, obviously, and then talk about the large-scale gas kinematic properties we obtain with our observations. Then I will talk about the dense core population and how we can have some insights on their extinction with the gas, and finally conclude with a perspective and my conclusions. So first, the Pipe Nebula, you can see it here. It's highlighted by this yellow box. Katja talked a little bit about this cloud before. It's a very nearby cloud, around 163 parsec from us. And it's very easy to observe it because it's at low latitude, so we can observe it with both IRAM and with ALMA. So it's very interesting to observe this cloud. Very early in the observation process and in the literature, we see that the Pipe Nebula was separated in 3 different regions. So you can see them highlighted in this airshell map, so the dust emission map here. You have the first region, which is called the ball, which have some dense filaments and less dense filaments and some young dense core. You have then the stem, which is in the middle here, which have the least dense filaments of the Pipe Nebula, and some few dense core, but very few. And finally, B59, which is the only region of the pipe where you have stars, and with high density dust. As you can see here, you have a big, massive dust extinction and emission. And so the main question that was raised by the observation of the pipe, the main first question was, why do we have these different properties of star formation across the pipe? So here I show you the polarization angle of the Pipe Nebula. Katja talked to us a little bit about the polarization angle of the pipe, so I will not learn anything to you today about that. Just to quickly summarize it, on the left you have the polarization angle in black with this black line on the airshell map I showed you before. And as you can see, the polarization angle are very well aligned across the pipe, all across the pipe. And if you zoom in this specific region, so it's at the limit between the ball and the stem regions, you will see this kind of polarization. So here you see the place where you have the lowest dispersion of polarization across the pipe, which is about 2.4 degrees approximately. And as you can see, all of the other fields in this region, all of these other measurements of polarization angle are quite the same, are quite well aligned, except for this one, and they all have low dispersion. And if you worked on the Davis-Chandrasekhar-Fermi equation, and if you used it, because it's proportionally inverse to the dispersion angle of the magnetic field, you will understand that we are maybe looking at a very high or strong magnetic field intensity molecular cloud. Now about the dense core population of the pipe, it was one of the earliest molecular cloud observed, dense core observed, and for now, we detect approximately around 200 dense core across the pipe that are highlighted here in this dust extinction map, one of the first dust extinction map produced. And this allows to produce, to work on the core mass function and compare to the interstellar mass function. Again, I will not learn to you anything, but just to remember, this cloud was one of the first that were used to compute the EMF and prove with other molecular cloud that we have a core to star formation efficiency of around 0.40. So to summarize a little bit, the Pipe Nebula is a very important molecular cloud, very interesting because it's nearby. It has important properties in terms of dense core and in terms of star formation, and also the magnetic field is well known and very specific to this region. So these are the reasons why we decided to observe this molecular code and to produce 120120 map of this region, of a specific region. On the left, in the color map, you have on the top and on the bottom, these are the same color scales. You have the extinction at the visual band of K, produced based on Herschel and Planck observation by Eisenberger 2018. So we decided to observe in this specific region, so you can recognize maybe the ball here, the stem which is here, and the B59 region here. And we decided to observe at the limit of the ball and the stem. So why we decided to observe at this specific region? Because it's where the polarization angle is the lowest, the dispersion of the polarization angle is the lowest, and also because there are here two velocity components that are overlapping in this region. That's something that we know since the first observation of the pipe, and that was proposed to be a converging flow by a difference paper. So we produce the largest 12CO map at this resolution of the pipe. So it's the contour highlight here. And we also observe the different dense core that are in this field at multi-line observation. Our map, in fact, covers different extinction. As you can see here, we are between 0.5 and 5 magnitude here on extinction to probe the more dense structure and the more diffuse structure of this place. The main idea here are to work first on the structures about in this map. So they analyze these structures by their with respect to the magnetic field orientations, and then to work on the dense core, the different dense core across this region, and understand that physical condition and properties. One of the first results we obtain is highlighted in the left figure here. So in background, you have the 250 micron Herschel view. And on top of that, I plotted different spectra of our 12CO map. So first thing that you can see, the spectra here are average in a specific region. You can see that we have two types of spectra, mainly. We have one type, which is highlighted here, with one velocity component. We have another one region like that here. And all of the spectra in this region are almost centered at 3.5 to 4 kilometers per second in velocity. And the second type of spectra are in this diagonal here, contains multiple velocity components. As you can see here, you have velocity components. You can see also here in this spectra here that are centered at velocity higher than 4 kilometers, higher than 5 kilometers, almost on this region. And these, in fact, are trace the two velocity components seen before by others' paper in 13CO. On the right, you have an extinction map. On top of that, there are the 13CO contours observed in 1999 by Onishi. And the contours are in white for the velocity component at 3.5 kilometers per second, approximately like the velocity component we saw here. And in red, the velocity component at 5 kilometers per second, which are the second velocity component we see in the top of our images. So we are really probing this interacting region with our observations. Now what we can see, if we look at different velocity channels, I just selected few ones of the velocity channel because there are a lot. What you can see is that these structures are in fact connected in velocity. So the two first channels here are lower than 4 kilometers per second. So this corresponds to the components here in white. And the two on the bottom are at higher than 5 kilometers per second, or at least the last one, and so probe the other velocity components. The thing you can see here is that they are connected in velocity and in space because you have at low velocity one main component here, another one at least emission here. The component on the top will disperse at higher velocity at 3.4 kilometers per second, but let's place to another big emission here with another very emissive with a lot of high intensity here emission, the maximum of intensity here. And then the two components will come together at 4.3 kilometers per second, will form only one component. And finally, if you look at the high velocity component, you will see that the main orientation of the components are perpendicular to the other one, and because they are oriented in this direction. The main thing here is that on the large scale, what you see is that we have one main component here almost parallel to the magnetic field given by these purple lines. And at lowest emission, lowest velocity component, you have brightest structures, but they are unrelated to the magnetic field. When you look at small scales, we made high identification structures, and we detected some elongated structures which spans almost 0.2 kilometers per second, which are 4 channels. And we also detect some narrow filamentary structures with transverse size almost 16 milliparsec. Now, if we look at the magnetic field and at the orientation of the structures with the magnetic field, what we saw as a preliminary result, we need still to work on a little bit on which structures are real and how they and if they are coherent between each other. The first preliminary result we see is that almost the half of them are aligned or perpendicular to the magnetic field. There are almost around 40% that are aligned and 10% that are perpendicular. And the rest, so the half of them, are neither aligned nor perpendicular to it. And in fact, the low brightness structures, the structures that are seen in the highest velocity map, in the highest velocity channels, are in fact rather well aligned with the magnetic field, like you can see on this plot. And so we know, and Katja talked to us about that before also, when the dust filamentary structure seems to be well aligned with the magnetic field when they are diffuse, when they are a low density, and mainly perpendicular to it when they are at high density. It was shown also in MHD simulation, like I shown you here on this work of Soler and Nebel in 2017, where you have here this parameter that gives you the orientation with respect to the magnetic field of the different dust structures they analyzed. And so when this parameter is positive, you are parallel. The structures are mainly parallel to the magnetic field. And when it is negative, these structures are mainly perpendicular to the magnetic field. And you can see really well this tendency where you have low density structures, in fact here, that are mainly parallel to the magnetic field, and the highest one that are mainly perpendicular to it. So what we are seeing here with these preliminary results is that we are maybe probing a transition from aligned to perpendicular structures, so to a densification, in fact, process of filamentary structures. Now, if we want to put some numbers on the magnetic field intensity, we used, because we are in a compressive field, we use the last estimation, the rework and the Davis-Chandrasekhar Fermi equation of the magnetic field intensity by Skalidis, which in fact give us that the magnetic field is around 20 microgauss with a lot of uncertainties because of the measurement of the density of the measurement of the dispersion of the velocity. And so we can also compute the Mach number, which is around 7. And these results show us that these are still also preliminary results, but they show us that we are in a medium in a region with a strong to medium magnetic field intensity. Now, a couple of slides about the dense core study we made. On the left, you have the dense core observation we obtained. So you have on each column the dense core, so given by their name on the top. And each lines are different molecular transitions. On the right, you have the same map I showed you before, where you have the position of each of these dense core. The things you can see with this red arrow are that we see multiple velocity components on multiple dense core in C18O. We also can see that on some place we have broad, so large 12CO emissions, which don't have counterparts in 13CO nor in 12CO.
Simon, you have 3 minutes left.
Sorry, how many?
You have 3 minutes left.
Okay, great. And so you can see also in the yellow one, sorry, that we have no counterparts in 13 and 13O for some 12CO emission. And so this trace may be local maxima of extinction of dense core, or maybe we are seeing at two superposition of structure with one that are low, that have less dense structures. Finally, we can also estimate the gas column density. So very briefly, we compute Gaussian fitting on each of the C18O component of our dense core, like you can see on the top. And with some simplifying assumption, obviously, we can obtain an idea of the extinction value of this dense core. In fact, we are probing dense core that have extinction value between 0.05 and 6 magnitude, to be quick. And so we are not looking at core sample that are really dense core because we are lower than the 10 magnitude generally taken. And so again, we are wondering if we are really looking at real dense core or transient one or the young starless core. So my last slide, what are we looking at this dense core and why are we looking at this is because there are a lot of implications about the core mass function of the pipe. On the left, you have a summary of the mass obtained and computed on the different core here. And as you can see on the literature, the values determined are very different across them. Specifically for this one, for 54 core, for the core 54, sorry. And so, as you can see, the mass are between 7 and 0.4 solar mass. And so we are here in this very important, in one of the most important parts of the CMF, on the break of the CMF. And so it's the reason why we need to have better idea of the dense core mass of this region. So my conclusion about this work, very quickly, we present here the first large-scale map of the Pipe Nebula on this non-star forming region of the Pipe Nebula, which is highly dynamic. We firstly, for the first time, we show that there are connection in velocity space between the two structures, the two gas structures that were seen before. We also see a lot of structures along our map, which were almost where the majority or the half of them are never aligned or perpendicular to the magnetic field, which leads us to think about a transitioning region where the filamentary structures are becoming denser and denser. About the dense core, I show that we have low extinction dense core and that we are maybe looking at projection effects or to transient structures. What we have to do next is to work a bit more on the characterization of the filaments, estimate their density, obviously, of the different structures, and work on the large-scale coherence, like I said before. And about the dense core candidates, we need more observation of other molecular transition that we will be made next week, in fact, and obtain new estimate of the mass from the dust and the gas. And so I conclude on that, and I thank you for your attention.